Hello everyone, welcome to Prakriya Educations. I am Mallikarjuna. In this module, we shall discuss about the concept binary operations. In our earlier classes, we have come across various kinds of operations like addition, subtraction, multiplication, and division. The main property of these operations is that for any two given numbers A and B, A plus B denotes the sum of the two numbers, A minus B denotes the difference of two numbers, and A into B denotes the product of two numbers, and A by B is the division of the two given numbers with the condition B not equal to 0. You can also note that only two numbers can be added or multiplied at a time. If three numbers are given, for example, if you are having 3, 2, 5, then if we need to add all these three numbers, even then we have to first take any two numbers at a time, add these two numbers. Then for this result, you need to add the third number, and this will be our final result. And hence, you may conclude that addition, subtraction, multiplication and division are some of the examples for binary operations. Here, binary refers to. Look the formal definition for a binary operation. A binary operation star, usually denoted as this, on a set A is a function star from A cross A to the set A itself, and we denote star of A comma B, which is equal to A star B. Also remember that if the number of elements in the set A is equal to P, then the number of elements in A cross A will be equal to P into P, which will be equal to P square. Then the total number of binary operations from A cross A to the set A is nothing but a function, and hence you can remember that the number of functions from the set A to B is given by n of B whole to the power of n of A. Now here you may observe in the place of A you are having A cross A, and in the place of B you are having A, and therefore the total number of binary operations will be number of elements, what is the second set, that is B, to the power of number of elements in A cross A, and hence you will be having the number of elements in A is given as P to the power of the number of elements in A cross A is P square. This is the total number of binary operations from A cross A to the set A. Look at these definitions. The first one is the commutative law. Operation star on A is said to be commutative if A star B is equal to B star A for every A and B which belongs to the set A. The second one is the associative law. Operation star on the set A is said to be associative if A star B star C is equal to A star B star C for every ABC belongs to the set A. The third one is the existence of identity element. Given a binary operation star from A cross A to the set A, an element E which belongs to A, if it exists, is called identity for the operation star. If A star E is equal to E star A, gives back the same element A for every A which belongs to the set A. The last is the existence of inverse element. Given a binary operation star from A cross A to A, an element E belongs to A and an element A which also belongs to the set A is said to be invertible with respect to the operation star if there exists an element B which belongs to the same set A such that A star B is equal to B star A is equal to the identity element E, and B is called the inverse of A and also denoted by B is equal to A inverse. For each problem, we shall verify whether the operation is a binary operation and also verify whether it is commutative and associative, and also find the identity and inverse elements if it exists. Now look at the first problem. On the set of natural numbers, they have given the operation as A star B is equal to A plus B, which is nothing but the sum of two given numbers. Now plus is the operation from n cross n to the set n given by A star B is equal to A plus B. And you know that if you are taking any two numbers randomly from the set of all natural numbers and adding those two natural numbers, obviously we get back a natural number, and hence you can conclude that the operation plus, that is A plus B, is a binary operation. Mathematically, we write it as star carries each pair A comma B to a unique element A plus B in the set of all natural numbers, and hence we can conclude that star is a binary operation on the set of natural numbers. Now moving for the second one, that is to verify whether the operation is a commutative. According to the rule of commutative, we have to prove that A star B will be equal to B star A. Now let us start with the first, that is LHS one, that is A star B. Now A star B is defined as A plus B. This is our LHS. Now for the RHS, we have B star A, which can be written as B plus A, which in turn is nothing but A plus B. We already know that if you are adding any two numbers in the reverse way also, we get the same number back, and hence from LHS and RHS, that is equation 1 and equation 2, we have proved that A star B is equal to B star A, and hence we can conclude that star satisfies commutative law. Now moving for the third one, that is the associative one. According to the rule of associative, we have A star B star C should be equal to A star B star C. Now again starting with the LHS, that is A star B star C. A star, keeping it as it is, and applying B star C, the operation, we get B plus C. In the place of A, you are having B. In the place of B, you are having C, and hence applying the operation. Now you can observe that in the place of A, you are having A here and star. In the place of B, you are having B plus C. Now again applying the same operation. In the place of A, I am writing back A itself. Then you are having plus, plus. In the place of B, we had B plus C, and hence we can write B plus C, which in turn gets us A plus B plus C. This is your LHS. Now for the RHS, A star B star C. Now applying the operation for the elements within the bracket, we get A star B is nothing but A plus B, star remains as it is C. Right? Now again, as we had done in the LHS, in the place of A you are having A plus B, and in the place of B you are having C. Fine. Now in the place of A, applying this, in the place of A we had A plus B. After A we have got operation plus. Then in the place of B we had C, and in turn which gets us A plus B plus C, which is our RHS. Taking it as equation number 2. Now from LHS and RHS, that is equation 1 and equation 2, we can conclude that A star B star C is equal to A star B star C. Now we shall move on for the fourth one, that is the existence of identity element. Let us consider E is the identity element, and as per the law of existence of identity element, we need to prove that A star E is equal to A, and E star A should also get back A itself. Now taking the LHS, that is A star E is equal to A, applying the operation we get A plus E is equal to A gets cancelled and we'll be left with E is equal to 0. But now there is a problem because the set is being given as N and 0 does not belong to the set N, and hence you can conclude that there is no identity element for the operation star in the set N. And since the identity element does not exist, obviously inverse element also does not exist. Check the second problem. The same operation A star B is equal to A plus B, but on the set Z. You may also conclude that if you are taking any two integers and adding those two integers gets back an integer again. This is the pre-known result, and hence we can conclude that star is a binary operation on the set Z. And also, as we had done in the previous problem, we can also verify that star satisfies the commutative law and also satisfies the associative law. Now the leftover one is the fourth one, that is identity element, existence of identity element. According to the condition, we have A star E is equal to A should be equal to E star A, where E is the identity element. We shall now start with the first part of the equations, that is start with A star E is equal to A. According to the operation, A star E will be A plus E, which gives back as A. A and A gets cancelled and we'll be now left with E is equal to 0, and now 0 belongs to the set of all integers, and hence you can conclude that 0 is the identity element of the operation A plus B in the set of all integers. You may also check for the other equation, that is E star A is equal to A. We get E plus A, which is equal to A gets cancelled and again left with E is equal to 0, which belongs to Z, and hence now you can conclude that 0 is the identity element in the set of all integers for the operation star. Now going on for the last one, that is existence of inverse element. According to the condition, if A is an element, then A inverse is denoted as the inverse of the element A, which gives back us the identity element back, and even the reverse. Starting with the first part, that is A star A inverse is equal to E, and according to the operation A plus A inverse is equal to E, we have already found out that it is 0. Now A inverse is equal to, shifting A to this side, we get minus A, and you know that if a positive number belongs to the integer set, then the negative number also belongs to the integer set, and hence minus A also belongs to the integer set. You can also observe with the second part, that is A inverse star A, which is equal to E. Applying the operation, A inverse is equal to minus A, and hence now you can conclude that if A is an element of Z, if A belongs to the set of all integers, then A inverse, which is equal to minus A, which also belong to the set of all integers, is the inverse element under the operation star. If the question is on the set of all real numbers, again with the operation A star B is equal to A plus B, even then you can apply the same procedure to verify all the 5 properties. Look at the next problem, that is the operation defined on the set of natural numbers, and A star B is equal to AB. Now Since we know that in the set of all natural numbers, if you are taking any two numbers and multiplying those two numbers, we get back a natural number itself, and hence we can conclude that star is a binary operation on the set of natural numbers. Now, for the commutative law, taking the LHS, that is A star B will be equal to AB according to the operation, and B star A, which is BA, which is in turn AB itself. Therefore, from these two equations 1 and 2, you can conclude that A star B is equal to B star A, and hence we can conclude that star satisfies the commutative law. Now, moving for the third one, that is for verifying the associative law. LHS, we have A star B star C, where B star C can be replaced by BC according to the operation. Again, in the place of A you are having B, and in the place of B you are having C. A, that is B, B, that is C. Therefore, we get B into C. Again, applying the operation, in the place of A now you are having A, and in the place of B you are having BC, and therefore A into BC, which in turn gives us ABC. In the same way, we can also check that RHS also gets back ABC, and hence from these two equations 1 and 2 you can conclude that star satisfies the associative law also. Now, coming for the identity element, we have the condition A star E is equal to A, which gets back E star A. Now, coming for the first part of the equations, that is A star E is equal to A. According to the operation, A star E will be AE is equal to A, and A gets cancelled and we'll be left with E is equal to 1. And obviously 1 is an element in the set of natural numbers. Again, you can also verify with the other part of the equation, E will be equal to 1 again. And therefore, now you can conclude that 1, which belongs to the set of all natural numbers, is the identity element under the operation star. Now, we shall move for the inverse element. According to the condition, we have A star A inverse should get back us the identity element. The second part is A inverse star A. Now, let us have the first part of the equation, that is A star A inverse is equal to E. According to the operation, we can write it as A into A inverse, which is equal to A is nothing but 1. Now, A inverse will be equal to 1 by A, but now there's a problem because 1 by A, which is of the form P by Q, is not in the set of natural numbers, and hence now you can conclude that therefore no inverse element for the binary operation star in the set of all natural numbers, and hence for the multiplication, that is product of any two numbers, we can verify that it is a binary operation. It satisfies commutative and associative law, and also the identity element 1 exists in the natural numbers, but the inverse element do not exist in the set of all natural numbers. Check out the next problem. The same operation A star B is equal to AB, but on the set of integers, or you may also apply the same problem for the set of real numbers also. You can observe that the product of two integers is an integer and the product of two real numbers is also a real number, and therefore you can conclude that star, which is defined as AB, is a binary operation on the set of integers and as well in the set of real numbers. And also in the same pattern as we had done in the previous problem, you can also verify that star satisfies commutative law and also associative law. Coming for the existence of identity element, you can also observe that E is equal to 1 belongs to the integer set as well as in the real number set, and hence 1 which belongs to integer or the real number set is the identity element under the operation star. Coming for the inverse element now, A inverse is equal to 1 by A. This belongs to the real numbers, and again there is a contradiction that A inverse is equal to 1 by A does not belong to the set of all integers, because in the set of integers we don't find a number like P by Q form, and hence you can now conclude that there is no inverse element in the set Z under the binary operation star, but inverse element do exist in the set of real numbers. That is, if A belongs to the real number set, then an element 1 by A also belong to the real number set R, and therefore 1 by A is nothing but the inverse element of the element A, and hence 1 by A is inverse of A in the set of all real number set R. You may now conclude that in the set of natural numbers and in the set of integers there is no inverse element, but in the set of all real numbers the inverse element do exist. That's all for the day. In the next module, we shall solve some more problems on binary operations. Hope you enjoyed the video. Please don't forget to like, share and subscribe. Thank you.